they had for me was from almost 20 years ago. So I have a little bit more experience and gray hair than that picture showed. Things have already been largely talked about with the previous presentations. You know, it is not possible to inspect or to enforce safety at the end of something. It has to be designed into your systems right from the get-go. How do I advance the slides here, Chris? Oh. We're getting a noise that says, "Don't push this button." Okay, the first step in engineering any system, whether it's a computer, whether it's a rocket, ground support equipment, etc., is we have to define the requirements of the system. If we don't define the requirements effectively, the system is not going to give you the performance that you need. So first step is, what is the purpose of the system? As we've talked about some of the things, you know, you're going to have an overall system and you're going to have subsystems. So, for example, if you're burning liquid oxygen in your rocket, you may have a ground support system that involves how you manage getting LOX from the ground support successfully into your rocket at the conditions that you're going to need. We're going to talk about the performance requirements. What are the pressures, temperatures, flow rates, safety considerations, all of those types of things. And how will you operate your system? Are there going to be parts of it that are manually operated? Are they going to be all computer operated? Are you going to automate things? Again, it kind of goes into the purpose, the safety hazards, and how your group defines the requirements for that system design. We're going to go through an example of a system, engineering a system. The purpose of this hypothetical system is to supply a mixture of hydrogen, oxygen, and carbon dioxide to feed a bioreactor for biofuel and bioplastics research. The performance of the system requires that these propellants be well mixed before they're supplied to the reactor, and the relative concentrations are shown there. We also need this to be a low-cost system. Obviously, there's some safety considerations given that you have a combustible gas mixture, and part of what's driving the cost or the types of operations is they want these to be manually operated. There's no infrastructure in place to deal with that. So based upon the information about this hypothetical system that I could find online, propellants are going to be supplied directly from gas cylinders. And so I created a plumbing and instrumentation diagram here to basically show how gas cylinders could be connected to this, this mixing tank. In this particular case, to meet the requirements of the system, the mixing tank can operate at low pressure, and by simply putting a very accurate pressure gauge on the mixing tank, we can fill it by partial pressures, right? So if we use a vacuum pump to pull a vacuum on the mixing tank before we fill it, we can start with an empty tank, and by setting the pressure regulators on the carbon dioxide, hydrogen, and oxygen cylinders, we can sequentially load regs, open valves to fill the tank to a certain pressure. As long as you can do the math to calculate what pressure you want in the tank after each step of loading, you can very accurately load the appropriate mixture. And then by having the mixing tank then isolated, you can leave time for diffusion to thoroughly mix and remanipulate valves to feed your bioreactor. This system was actually implemented at the University of Hawaii in Manoa. And there you can see some photographs of the setup. The pressure rate, the cylinders with pressure regulators, and you can kind of see at least what we could find of the photographs. They've got some tubing going from the pressure regulators. There's only, we can see on the pressure tank that there's a relief valve coming off the side of the tank, a single line with a valve where the mixtures or the individual gases come in and the mixture goes out on the top, and presumably a very accurate digital pressure gauge on the tank itself. So how did the system perform? It was horrific. According to the accident report, the pressure tank exploded when the grad student pressed the off button on the pressure gauge. She was seriously injured, and in my estimation, obviously fortunate that she escaped this situation with her life. The laboratory was hugely damaged. The university was fined. And what I think is really interesting is that the accident investigators determined that the root cause was due to the fact that the digital pressure gauge on the tank was not intrinsically safe, right? It was not designed to be used in an explosive environment, okay? If the folks involved in that work did not understand that hydrogen and oxygen are highly reactive with each other, this could have been a completely plausible situation. The fact that they didn't know highlights, a serious lack of good judgment, good sense, good engineering, etc. We're embarking here on, these were the propellants that are directly, potentially a part of what we're all planning to do with this Base 11 rocket challenge, right? And so Base 11 is putting us forth with this safety training to try to help make sure that folks that don't yet have experience can become aware of all the various hazards and things associated with what's going on. So examining the system carefully for hazards, to assess the hazards and to assess the risks. There's a completely rigorous line of engineering to perform failure modes and effects analyses of things, to evaluate systems, designs, and so forth. Every company, every agency has their own spin on it, but it's a part of what you're going to need to accomplish, whether you call it an FMEA or not, but it's part of what's going to happen for your systems as you define your requirements and go through the engineering of them. One of the things that we want to do as we review our designs is challenge our assumptions. In the case of this particular experiment, they assumed that they needed to get a well-mixed feedstock for their reactor, that they needed to put it all in the same tank. Okay, with the rocket engines you're designing, right, you're going to be providing extremely well-mixed oxidizers and fuels. Are you going to create a large volume of that to feed into your rocket engine? I hope not. We're going to come up with a precise way to meter those flows real time to feed into the reactor in a controlled fashion. If for some reason you need to create a large volume of the mixture, obviously that creates some significant hazards, which we saw the results of. So if there is a reason to need to mix those, what could we do, right? We could engineer a tank that would survive the reaction if in fact it reacted. Or we could put the tank in a reinforced concrete space that if it fails, no personnel get injured. Or do the same thing with proximity away from people, right? There's lots of different engineering approaches to solve the problem. And so as we start looking at things, we want to challenge our assumptions about how and why we're doing things and evaluate why we're doing them, and is there a better or different, safer way. About the best way to help challenge your assumptions and to make sure you're not missing hazards is to invite experts to participate in the review of your design, right? The whole premise of this building rockets is cool. It's fun. You don't want people to tell you how to do it. You want to figure it out for yourself, which is why we're all here. However, after making the first cut in the design of figuring it out yourself, now you want to present it to folks that have done it before and probably done it wrong. And so they've learned, that's why they're experts, to review and ask questions and give you, it's not, we don't want to have people telling you what to do, but you want to have some pride in what you've come up with as a design and let people challenge you on your assumptions and your calculations and what you've done. And that iterative process is where we advance the art. As is very evident in this failure at Hawaii, finding experts with relevant experience can be difficult. Even the accident investigators said, hey, this accident was caused by the poor selection of a pressure gauge. And hey, you didn't wear the proper PPE. There's a whole list of things that they came up with that resulted in the $115,000 fine. The root cause was bad engineering. There's no point in mixing combustible gases in a pressure tank. That was lost on all of the people associated with when you read the accident report, and I've got the link to it there. So we want to try to bring in relevant experience and experts to help you, and that this meeting is just the start of that. Okay. Okay. From my perspective, the first step in designing the liquid propulsion system starts with the plumbing and instrumentation diagram. Plumbing and instrumentation diagrams are not unique to propulsion. If you're building a building or any type of thing that has plumbing, fluid systems, there's going to be a P and ID. I found when I say P and ID here at Purdue, you end up with all kinds of different things for what P and ID, what that acronym is. It's a plumbing and instrumentation diagram. It's going to tell you how you get the propellants or the gases, the fluids from point A to point B in your system. You're going to lay out your fluid system components based on what your system performance requirements are, whether or not you need to control pressures, control flows, etc. Once you design your plumbing and instrumentation diagram, it's going to give you a structured way to identify all of the different fluid system components in your system, okay? And help you define the requirements for each of those fluid system components, which you need to do before you can start contacting vendors or looking through where you might be able to scrounge hardware, etc. The PNID is what basically allows you to do the failure modes and effects analysis and to identify the hazards. Are propellants going to be able to come into contact with each other in places where we don't want them to? Are we going to be able to control the pressures, relief devices, all those types of things? And then the PNID is what you have to use when you actually write your test procedures, right? In order to say, hey, I'm going to get the propellants from the tank to this place, to this place, to this place. It's literally the plumbing and instrumentation diagram that you look at as you write your procedures to go through. So you have to start with an excellent design, hopefully reviewed for your PNID. So I'm going to go through an example of designing the lock system for a static test. This is how we would do it here at Zucrow Labs at Purdue. And it's not the only way to do it, but I think going through this as an example can give you some background about how one good way to approach it. So requirements for this system. We want to supply a controlled flow rate of liquid oxygen to the valve at the inlet of the rocket injector manifold. And we're basically going to say, hey, possibly your combustion chamber pressure may be 500 psi. There's going to be a pressure drop through your injector, through the valve. And so the pressure upstream of your valve, the system has to be able to supply 600 psi to that location, okay? And it needs to be a controlled flow rate. I'm not saying that we're controlling the pressure. I'm saying we're controlling the flow rate. You can't do both, okay? The pressure at the inlet to the injector, to the inlet of this valve, is going to be chamber pressure plus your injector pressure drop, okay? If you want to control the pressure to be 600 psi to the inlet, then you can't control the flow rate because you're going to have to keep either increasing or decreasing the flow rate until you achieve the pressure that you want, okay? There's a discontinuity there. So requirements are very specific in how you engineer your system. Pardon me. We have a static test duration that we want to do. In this particular case, arbitrarily, I said 30-second test. So that means the volume of your LOX tank has to contain enough propellant to allow you to flow at your desired flow rate for the period of time. We want to provide cold liquid oxygen to your test article without chilling your test article. Maybe you have some elastomeric O-rings, maybe you have what do we call it? What kind of chamber did you guys have? A ablative chamber that you don't want to freeze or saturate with liquid oxygen. So there may be any number of reasons why you don't want to flow your propellants through your injector to chill in your plumbing system. So we have to come up with some way to chill in your plumbing system without going through your test article. If in the event that your test article, your engine, blows up or has some sort of failure, we want to make sure that we don't have to dump the entire contents of the run tank out onto the ground or into the fire or whatever the case may be. And I think this would be true in all cases, whether it's a rocket or a static test, but we need the system to fail safe. We need to be able, if everything goes wrong, if something's not happening in the way you expect, you should have a simple, straightforward means of safing your system. And in our case here at Purdue, like we talked about on the tour, we fail safe by killing power. If you kill power, everything goes to a safe condition because no power is a very achievable state. If you guys have questions at any point in time during the presentation, please speak up. I'd like this to be, I don't just be up here talking at you. Please, if something's not clear, if I say something that doesn't make sense, please stop me.
Okay.
Yes.
So I do a hard time, I really do bad at pretending I know something. So be it that I come from a physics background, some of your acronyms I may not be familiar with.
Okay.
So just throw out an acronym every now and then.
All right, very good. So I defined plumbing and instrumentation diagram, PNID. LOX is liquid oxygen. I'm not sure what other acronyms I had to this point.
It was just sort of
okay, just in general. All right, very good. So to start the development of the plumbing and instrumentation diagram, we need a LOX tank. That's the first item. We are going to need a valve to turn the flow of liquid oxygen on and off to the test article. And then obviously we have the test article. In most cases, the folks designing the engine, right, are going to want to know the pressure and temperature of the propellants coming into the engine. So I went ahead and added pressure and temperature there. As we develop the PNID, if you add a component to the PNID, it's a good discipline to okay, yes, we obviously need a valve to turn the LOX on into the engine. But it's a great idea to try to document the reasons why you add that component to your system. It may be very obvious as you do it at the time, but as your system, as all the elements get added to your system, as things grow, it's always good to be able to go, okay, why is this component in the system? And because particularly in this environment where your collaborators are potentially part-time and you may have turnover in your groups, it's going to help with the education and carrying the corporate knowledge forward. So in this case, what I called valve 1 is our LOX run valve. In order to fail safe, we probably want this valve to be normally closed. We want to intentionally have to open it. Most of the time, we want our propellant valves to be as close coupled to the engine as possible, right? We want, when we open the valve, to have flow going into the engine in a precisely consistent time. So by close coupling it, it allows us to do that. But by close coupling the valve to the test article, we recognize that this valve is at risk for being damaged if the test article fails. Question?
By close coupling, do you mean it's close to the test article with the line so there is the plumbing?
Yes, by close coupling, I mean close physical proximity. It basically means the volume of the plumbing between the valve and the test article is reasonably minimized. Is the sound on to where we'll hear if other people have questions remotely?
They should also have a message.
Okay, I can hear somebody remotely, so thank you. Did you guys have questions, Adam, or you just let me know that? Okay, cool. Okay, now to continue to meet the requirements for this system. To meet the requirement that if the test article fails and we want to be able to, and we need to be able to turn off the flow from the test stand to the test article, we added valve number 2. And now valve 2 is the lock supply isolation, and we're going to have that fairly close to the supply tank so that it's further away from the test article. And we're going to make it normally closed as well, so that if everything fails, we can simply kill power to fail safe. I didn't know anything about cavitating venturis when I was a student, so I don't know where you guys fall in that. But obviously, depending on where you are in your freshman to senior, you won't know about a sonic venturi until you take compressible fluids. But a sonic venturi, it's called a sonic venturi because the gas going through it will accelerate when the flow contracts going to the throat. It's going to accelerate until it gets to a critical pressure ratio where it's choked. Okay, and once you choke the flow rate through the orifice depends only on the upstream pressure and temperature conditions. So you can have a sonic venturi that's choked with, if you've got 1,000 psi coming into the venturi, the pressure downstream of the venturi could range from vacuum to 800 psi, and the flow rate through the venturi would not change. So you can completely decouple the flow rate from anything that's going on downstream. It's a really awesome device. It basically allows our propulsion devices to function. But it's a cool device to use in a ground test propulsion system because it allows you to very precisely control your flow rates by simply using your facility pressure regulators to control pressure. Well, there's a similar device for liquids called a cavitating venturi. The physics are different, but functionally it's the same. If you use a venturi with a throat sized appropriately, you can control the pressure and temperature. Basically, you size the throat for the temperature of your fluid based on the density. You have to make it allow you to stuff the right amount of mass flow through it. But by simply controlling the pressure upstream of a cavitating venturi, you can control the flow rate independent of the pressures downstream. So if your combustor, if you intend your combustor to operate at 500 psi and your combustion efficiency is such that it only operates at 400 psi, you won't have to have, your flow rate won't be higher than you expect, because with a cavitating Venturi, you can control the flow rate and get exactly the mixture ratios or the propellant flows that you want. So because in the requirements we specified controlling 10 pounds a second, somehow we have to control the flow rate. And in this particular case, I elected to put in a cavitating Venturi. And so if we control the pressure in the liquid oxygen tank such that the pressure upstream of the Venturi is controlled, we'll be able to manage that. Now, in order to measure the flow rate, I need to know the pressure and temperature upstream of the Venturi. So we have to add that instrumentation. I'm not sure I articulated that very well, but hopefully that makes sense. Okay. We had another requirement that we not chill the test article. Okay. But if we have piping or tubing between the run tank and the fire valve, and that plumbing starts out at ambient temperature, it's a big heat sink, and it takes time for the liquid oxygen that you're flowing through your system to chill that plumbing down. And so it basically becomes a vaporizer and turns your LOX into a gas or into a warm liquid. And so by adding valve 3, I have a way to open a valve and allow flow to come from my liquid oxygen tank, go through valve 2, through the Venturi, and out to a dump, so that that plumbing can all be chilled in ahead of the test. You'll notice with valves 1, 2, and 3, if those valves are all closed, we have a closed section of plumbing in our system. And if we have that section of plumbing filled with liquid oxygen and we close all the valves, particularly if something doesn't go wrong, the computer crashes and we go to our fail-safe condition and all the valves are closed, well, we've started the clock on that liquid oxygen boiling off and basically building pressure in that plumbing until we get to the burst point, right? Something is going to fail. And so we have to accommodate, we have to deal with that design. So any place we could trap a cryogen in a system, we have to have a means of letting the pressure relieve. And so thus we added relief valve 1. Relief valve 1 is, the conditions for it are challenging, right? We don't want the relief valve to flow or relieve any fluid under normal operating pressures, but we need it to protect the plumbing. So we've got a distinction between our intended operating condition and the max rated pressure of our valves and tubing in the system. So we're probably going to want to set the relief valve cracking pressure to a pressure that is near the maximum of our valves and plumbing, not near the maximum of our intended operating condition.
Is there a rule of thumb with that difference? Like if it were, let's say 10,000 PSI, would your relief valve be at say 9,000?
So this, okay, so the question is, how do we determine the relief valve cracking pressure? What we have done here is cryogenic relief valves at pressure are challenging in our experience, challenging to have them work exactly the same all the time. So most of the time we will put the relief valve on a little bit of standoff plumbing so that unless the relief valve is cracking and opening and allowing flow, it's going to remain in ambient condition. So we'll put enough tubing between the location that the relief valve's installed, the connection for where we're connecting the relief valve to the location of the actual relief valve, we'll give some standoff plumbing so the relief valve doesn't get cold. And so now it's going to behave in a much more predictable, reliable fashion. Now, once that relief valve cracks and allows flow, it will reset, but the pressure that it resets at is a crapshoot until we know until basically the valve returns to ambient temperature. Generally speaking, we'll set the relief valve. In most of our cases, the valves are the limiting pressure. So if the valves have a maximum operating pressure of 1,000 PSI, we'll set the relief valve to 1,000. These are not an ASME code. This is your part of your fluid system. So this is more the B31.3 type of code requirement. We don't want to set the relief valve any higher than the components, but generally speaking, we can go right at the pressure.
If you trap, like say you have prior trap, you also worry about like power. You worry about the fact that valve loads.
So the question is, when we have the system locked up and the pressure is allowed to build, whether the relief valve cracks or not, once we have control of the system again, what's going to happen when we've built pressure in there prior to opening the valves? I haven't given that direct thought. Most of the time, our plumbing systems, we insulate them, but the insulation is poor enough that the heat leak is going to take away the locks well before we actually have been able to get control of the system again. And so we've not really experienced any incidences or things from that propellant flow slamming. But you're absolutely correct. That's a consideration that you have to think about. In this particular case, with the Venturi in the system, that's going to limit the overall flow rate through the system, and minimize the slam potential. But depending on the design of your system, you may or may not have that. So it's a consideration relative to when you open valve 3 to dump or valve 1 to go to your test article, the pressure is going to drop very quickly. And so obviously you need to make sure that the plumbing downstream can take whatever the momentum of the velocity of those fluids is.
Are relief valves able to handle something as dynamic as like a water hammer, or would there be? Because I'm worried about risk with nitrous oxide vapor, adiabatic heating. If we put like a relief valve in that line, is that going to crack in time? Something like that, or?
So using a relief valve to protect from water hammer would not be, in my opinion, a first choice to try to alleviate that. You want to prevent the water hammer in the first place.
Yeah.
So in the way this system is laid out, you'll notice the Venturi is upstream of the run valve, the fire valve. So the system will be completely wetted with propellant all the way to the run valve. Water hammer happens when you bring the fluid to a stop. Okay? It's the momentum of the fluid being slowed down that causes the water hammer. So in this case, with the system being fully wetted, when you open the run valve, the Venturi is limiting your flow rate right from the get-go because it's already wetted. So you're actually not going to have a water hammer with this arrangement with the Venturi upstream of your run valve. If the Venturi were downstream of the run valve on the test article side of things, when you open the run valve, you're going to have no fluid restriction until you get to the Venturi, and you will water hammer the Venturi.
But then, if say we slam valve on those, there would be a water hammer there, right?
There will be, but again, if your propellant lines are sized to have a reasonably low velocity, you're managing the momentum, right? Because it's mv squared. So as long as you've sized your propellant lines appropriately for the velocity, closing the valve should not create a significant water hammer. by the same token, to further improve the situation, you have other options, right? You can rate limit how quickly your valve closes, right? So most of the time what we use are pneumatically operated ball valves. And so in order to actuate a pneumatic actuator, you're letting gas in to push a piston. And when you go the other direction, you have to allow that gas to vent out to either let the spring return it or pressure on the other side of the piston to push it. So there's all kinds of options. You could use needle valves in the pneumatic control of your valves to control how quickly the piston can move and therefore how quickly your valve can either open or close. Thank you for asking these questions. I mean, this makes it much more interesting for me and hopefully more meaningful.
Go to the decision to do valve 3 as normally closed, or if there's a big difference whether we make that one normally closed or normally open.
So the question is the choice of making valve 3 normally open or normally closed.
Questions, right?
Valve 3 being normally open or normally closed. There are excellent, there could be excellent arguments to make it either. It's an excellent question, and I think I could go either way on it.
We have a question here at Long Beach.
Yes.
What's our question?
Will you be addressing the Fox particle impact later, or?
He has a question about LOX particle impact. Is that something that you want to address now, or it'll probably come up in our...
I can touch base on it just really quickly. Particle impact, so in oxygen makes everything highly combustible. Almost everything highly combustible. And to have a fire, you have to have an oxidizer, a fuel, and a source of ignition. In oxygen systems, particulate contamination in gaseous oxygen, if the particles are of the right material and they're moving quickly enough to where they don't make a turn in a bend or a fitting, they can impact tubing with enough energy to create a source of ignition. Particle impact ignition hazards do not exist in LOX, but they do exist in GOX because it's a heat energy from the impact. And so liquid oxygen, you're not going to be flowing, one, you're not going to be flowing fast enough to create enough impact energy, and two, it's at such a cold temperature, it's not an issue. So in designing the liquid system, generally speaking, we're designing for velocities that minimize the friction pressure drop to a manageable level. But it's a good point with respect to the velocities. LOX systems will have gaseous oxygen in them until they are cold. And so we want to pay attention to the rates that we build pressures and things like that when we're chilling to make certain that velocities don't create issues. Notionally, in stainless steel plumbing, gaseous velocities below 150 feet per second are not going to create risks of particle impact ignition. But you'll get that information in great, awesome detail from Joel Stoltz's presentation that the NASA has arranged for you guys to have access to. Just as a further endorsement, when I came to Purdue in 2001, I had no experience with oxygen whatsoever. My experience was all with 90% hydrogen peroxide. 800,000 pound thrust engines with hydrogen peroxide. So large systems, but not anything with oxygen. So when I came here and we decided to pursue oxygen and liquid oxygen, the first thing I did was go take the fire hazards and oxygen safety training from Joel. they teach it around the country periodically. And so the fact that the NASA and Base 11 have made this available to all of you, I think is a absolutely awesome situation. Okay, moving further into the system to meet the requirements. I'm sorry, we have another question. No, go ahead. Okay. All right. At this point, we basically are starting with a liquid oxygen run tank full of locks. We don't have any way of getting oxygen into that tank in the first place. So to address that, we need to add a supply of liquid oxygen. In most cases, particularly in the desert, we're not necessarily going to have a bulk supply of liquid oxygen. You're going to be working with locks from some sort of a trailer or dewar. And so the dewar will have a valve that lets the liquid oxygen flow out of it. So because the P&ID is going to have to reflect everything that you do in your procedures from fluid from point A to point B, we want to show the valves that even come with the containers or the cylinders that you're using. We probably, in this case, I elected that we're going to want to be able to operate the system by computer control remotely as much as possible. So we're going to add valve 5 to allow us to remotely control loading liquid oxygen into the system. Again, selected normally closed so that we can stop the transfer if necessary during any kind of issue. Again, now we've got a valve on a dewar and we have valve 5. So we have the potential to trap a cryogen between two valves. So we have to add a relief valve again. This relief valve is probably set at a much lower pressure because it's going to have to protect the valve on the liquid oxygen supply. And most of the time, the liquid oxygen dewars are probably going to have a 125, 250, or maybe 300 PSI pressure limit. So we want to make certain that we don't possibly back pressurize anything. The other thing is, if we look at this as a system, we're going to be pressurizing the liquid oxygen run tank to some sort of high pressure when we're pushing the liquid oxygen into the engine. No, as it's has been stated earlier, you can't count on any valve to function exactly like you want it to. So if valve number 5 happens to leak and we pressurize the run tank, we're going to be pushing high pressure oxygen back towards the supply. So now we have the additional requirement on that relief valve to not just protect from a boil off inside the line, but we also have to protect against a potential leak in valve 5. Okay. Now, depending upon what you guys decide to do from a safety perspective, you might also even have to consider the operator screwing up and opening valve 5 with the system under pressure. Right? If you've pressurized your LOX run tank, you have valve 2 open and valve 1 is closed and you're getting ready to fire your engine and somebody screws up and opens valve 5, well, now you've got pressurized oxygen going to a place you never intended it. So your relief valve is going to have to potentially overcome that failure.
You were mentioning that you automate your system with computer control. You have a logic that have if-then conditions such that if one given valve is open, the other would react. Kind of preventing that back.
So the question here is, with an automated system, do we try to idiot-proof it with programming code to prevent someone from opening valve 5 with the liquid oxygen tank pressurized? And the answer to that here at Purdue is that we do not. The systems end up complicated enough that keeping things working In that fashion, we've elected not to do that, so we do it with the hardware. But that is absolutely an approach that would be reasonable and that folks could pursue. And you wouldn't necessarily even have to do it with computer code logic. You could also have a pressure switch in your system that would not allow the electrical signal to open valve 5, to reach valve 5, if the pressure switch was open because the pressure was above a certain threshold. So there's lots of engineering ways to approach these issues. The key is to identify them and then figure out how to mitigate them.
Is it common practice to, during your test, use the supply doer attached, or is it common practice like put everything on fill and then take everything off?
So in the case of our large static test stand setups here at Purdue, we add another valve between valve 5 and valve 4 that is a normally open dump valve. So once we get done transferring, well, let me take that back. We add 2 more valves. We have a remotely controlled valve just downstream of valve 4 at the supply with a relief valve between there. And then we add another valve that's normally open that dumps the line. And so once we get done with the transfer, we close a valve and we open the dump, such that if valve 5 fails, leaks, whatever, the flow gets dumped to ambient rather than potentially going in. This is all part of engineering, is assessing, is meeting the requirements of your design, but cost is a big part of engineering. It's not necessarily. So you could add a tremendous number of valves to your system, and you basically have to go through what your hazards are and how you want to mitigate them for what's reasonable. The absolute safest thing to do with this, in my opinion, would be once you've finished loading liquid oxygen into the run tank, would be to close the door and disconnect the door from the system. If you can do that with your run tank filled and not pressurized, that's probably a reasonable approach. Depending on the scenario of your system, you have to assess the hazards and the options to mitigate it.
You know, some together, but I've seen examples where box shapers will be loading manually, like they'll be turning a manually operated ball valve to flow liquid oxygen into their pocket or into their engine pump tank for testing. And I'm wondering, like, in our system, we're designing then that everything will be done remotely, so we won't have to be at the system flowing oxygen tank, even though it would be at low pressure. Trying to avoid unknown hazards. If some component fails on the tank, that's possible. I'm wondering, is it like a safe practice to manually load the oxygen, or is that?
So the question is, is it appropriate practice to manually load liquid oxygen into the rocket versus having to basically setting up everything to do it with actuated valves controlled remotely? I don't necessarily. My personal preference is to set things up to operate with propellants as remotely as possible. Now, there's a tremendous amount of manual operations done with liquid oxygen, right? When all the valves on liquid oxygen dewars are manual valves. So liquid oxygen dewars are filled, but by using manual valves by the hundreds every day. So it's proper engineering to mitigate the hazards such that the risks are minimized. So if your rocket has been properly engineered and you can do the transfers and filling and keep pressures way below the operating conditions for your rocket while you're loading, I think it could be perfectly reasonable to do it manually. That is my opinion. You guys have to engineer the system, assess the hazards, and make sure that you drive your risks to a low acceptable level.
I'll just.
Oh, okay. We have found that you here at Purdue, generally speaking, painfully, that you almost can't have too many filters in your systems. Filtering things is extremely helpful to minimize, unintended debris from creating issues in your systems. But recognize filters are high surface area devices. When you think about if you're trying to light a campfire, you need to have a kindling chain, right? You need something that's easily ignited in order to light the larger material, in order to light the wood that you're likely to burn, right? So filters can be highly susceptible to a kindling chain type of situation. So you need to make absolutely certain that any component you put in your system is appropriate for the propellants, the pressures, the flows, but particularly so in oxygen. And so you're going to want to make certain that the filters that you pick are designed for use in oxygen, and that they are absolutely not possible to be fuel. So they're going to need to be brass and metal.
So is there like a good size for like the microns? Like how big is a reasonable size for the match? Like a lot of us probably don't have experience on like how fine should we be filtering out particles.
Without knowing exactly what the current today's oxygen safety training material is going to tell you, I'll just tell you that we use 10 micron. 10 micron nominal, which is probably about 20, 25 micron absolute. And we use filters from a Norman filter company. Reasonable cost, high pressure, short lead time, really, really excellent products. Okay. We have in this scenario, we found a way to bring liquid oxygen to the run tank. As was mentioned earlier by Adam, we're not going to get any liquid oxygen to go in the liquid oxygen tank if we don't have a way to let the gas that evolves out, right? So we're going to need to add a vent to the liquid oxygen tank. Now, the vent serves a couple of purposes. One, when we pressurize the tank to the desired operating pressure, at the end of the test, the tank's going to be pressurized. We need some way to vent the tank. At the same time, in order to get the tank chilled and full of liquid cryogen, we're going to need to be able to vent out the evolving gas. And so, with respect to fail-safe, we elect to put normally open vent valves on propellant tanks. That way, when the test's over, or if we have an issue, the tank is vented. Sizing the vent valve so that you can actually get liquid in at a reasonable flow rate to chill it is another consideration for that vent valve. In our cases, we don't have any way of measuring the liquid level in our liquid oxygen tanks. So all we do is fill them until they're overflowing. And the way that we know that it's overflowing is by a thermocouple on the outlet of the vent. There are ways to measure liquid levels in cryo tanks. One way could be head pressure. You can look at the differential between the pressure in the top and the bottom, and the only difference, if it's a closed system, is going to be the weight of the liquid in the tank. So head pressure is typically what's used to measure the volume in bulk tanks. There's floats, there's ultrasonic sensors, there's all kinds of different ways of doing it. But for low cost, in high pressure, relatively high pressure systems, there's not a really good, simple solution. And so simply overflowing the tank is the cheapest and easiest way to know that your LOX tank is full. The question is, what do we do with that, with the LOX that comes out of the tank while it's overflowing? And we evolved at that. If you look at videos from large test stands, they just dump that LOX into the flame bucket. They just let it overflow and stream into the flame bucket where there's probably water and certainly a lot of concrete, and that boils it off. We don't have that here at Zucrow at Purdue. So I won't give you the long story of all the things we did wrong. What we do is actually just dump it into a vaporizer. So we dump it into something that's designed to vaporize a cryogen. And so then we're just venting that LOX as a gas. That requires a fair bit of infrastructure to do. So I think if you could, with this chill, if you have an area that's concrete, and you have the ability to throw a little water on it, water has an awesome heat capacity. It's going to vaporize all the LOX you could possibly throw at it. But just simply going on to concrete is a reasonable way of getting rid of it as well. Okay, so we've got the run tank. Now we need some way to bring it to the desired operating pressure. And in this case, what we have done is pressurize the tanks with gaseous nitrogen. So we're adding a nitrogen cylinder. I added valve 7 just because that is the valve on the gas cylinder. It's a valve you're going to have to manipulate in your procedures. So I think it's a good idea to indicate that valve on your PNID. The pressure regulator that is supplying pressure to your LOX tank, I've identified as pressure regulator 1. The relief valve then, so then now we've got a source of pressure coming into the tank. We're going to close the chill valve or the vent valve to build pressure. We're going to need a relief valve to make sure that tank doesn't get overpressurized. Again, we tend to put those relief valves on a length of tube away from the tank so that the relief valve can remain at ambient temperature to improve its predictability and its performance. But you can never have any valves between a relief valve and a tank such that someone could accidentally close it. The relief valve has to be sized to the worst case source of pressure. In this case, you have to deal with the tank all being closed and the liquid oxygen boil off building pressure and needing to be relieved. You also have to deal with the possibility that pressure regulator 01 may fail open. And so you have to look at what the maximum flow capacity of that regulator would be with your maximum supply pressure and make sure that that relief valve will relieve all of that flow without taking your tank to the higher than rated pressure. If this is a static test setup, I would expect that your tank is going to be built consistent to the boiler and pressure vessel code. If it's obviously a tank that you're going to fly, you're going to have to come up with a rationale for your own safety factors. And I think base 11 is going to provide some suggestions for that. But if it's a static tank that's not flying, it should be a boilerplate per the piping or per the pressure vessel code. And that's going to dictate that the relief valve cracks at maximum expected operating pressure. The code is going to tell you what the allowable stress is for your material at your condition. You don't get to pick the safety factor. All you get to use is the allowable stress per the code for your material. And then, of course, we needed some way of measuring the pressure in the tank. So adding pressure transducer 3. Not sure when. Okay. Now we're down to the actual fluid system components, right? We've identified where we need valves, relief valves, pressure transducers, thermocouples, etc. Now we have an idea what the actual performance specs are for each of the. Now we have to basically pick components that meet the performance specs for where we're putting them in the systems, and the system components have to be able to take the maximum possible pressure to which they could be subjected when installed in the system, not what you intend the maximum pressure to be. So for example, we put the relief valve to keep the boil off from bursting valves and tubes. We need to make certain that we pick the relief valve set point to match what the components are. And that may mean picking components then that obviously all have, you're gonna have to set the relief valve to whatever the least rated pressure component is in the system, right? So if you've got 2 valves that are rated for 1,000 and one that's rated for 1,500, your relief valve is gonna have to match the 1,000. You're not gonna be able to use the full 1,500 PSI capacity of the third device. I've talked about the fail-safe several times. The way that we elect to achieve fail-safe in our systems at Purdue is we operate all of our valves with 24-volt DC solenoids. And so it's very easy for us to put our system into a safe condition because all we have to do is unplug the 24-volt power supply and the power turns off and everything goes to its de-energized fail-safe condition. We don't obviously literally unplug it, but we can kill the power. And now that we've got the components identified in the PNID, now it's straightforward to look at what the system requirements are in terms of flow rates, and now we can figure out, okay, what is the flow coefficient requirement, the CV requirement of a valve to have the appropriate pressure drop in the system to make sure that our lines are sized appropriately for the velocities, the propellants, etc. Now that you've designed your system, right, you have an effective PNID, you have sized all of your components, before you actually build anything and procure things, I would, what we do here is we'll engage the research sponsors from SpaceX, from NASA Marshall, from Stennis, from wherever we can draw the expertise, and we're going to review the PNIDs from a hazards perspective. And so I think, again, you don't want to feel like if you show that someone's going to be, you want people to challenge you on your design to make sure you've thought of everything. So reviews as frequently as you can manage, I would strongly encourage. Once you have approved your PNID, you want to come up with some way of saying this is what the system will be, and you don't let it get edited again. Okay, this is the document that defines your system. You need to have some configuration management control of that document. When you actually start building your systems, you're going to find that there's all kinds of pressures coming from different places to do things differently than you designed. And there may be good reasons to actually change things, but what you need to do is you can't just arbitrarily think about it, look at the PNID and make the change. You need to make sure that you go back through a rigorous re-review. And by having written down why you added your components in the first place when you put them in the system, that will help you to evaluate whether the suitability of a change. But make sure that you have a structured way of going about doing that. Question?
When you have, say, a tool at an outset that's supposed to contain are those systems segregated enough that you have separated out each or
So the question is, we just did the example of just a liquid oxygen system. Obviously, you're going to have a fuel system, and probably and obviously also a pressurization system that at some point is pressurizing more than both propellant systems. So this was a constrained example. You're absolutely right. You're going to need to go further back on the pressurization system side at the very least to see where things segregate and make certain that you have redundant ways to make sure that you can't get oxygen going back to your fuel system and fuel going to your oxygen systems. How you manage the documentation of those plumbing and instrumentation diagrams and so forth. If you happen to be in a situation where you're just starting and you're building up your system for your rocket program, I would put it all in the same document. Keep it as simple as possible to capture all of the information. That's what we did here at Zucrow when we first built up our first systems. At some point, as you add more test stands and more systems, that becomes to the point where putting it all in one document is no longer a simple way to understand what you have. And so it's an evolution. You're going to have to determine what works best for you and your situation, but in order to keep things clear.
Or with that, once it gets complex, is there any good programs or software that allow you to do very complex system design that you break down into that you can easily just go and check this instead of having a bunch of documents?
So the question is, what kind of software, or is there software or a means of effectively managing your plumbing and creating your plumbing and instrumentation diagrams, managing them, etc. I would not say that we are necessarily completely exemplary here. In our case, we started out doing P&IDs in PowerPoint, and then we switched to AutoCAD. And then it becomes not many students knew AutoCAD. And a lot of the other solid modeling programs don't necessarily do a great job of doing line things. And so we have evolved to using Visio. And Visio actually has a lot of templates for making plumbing and instrumentation diagrams and wiring diagrams and those kinds of things. And Visio is a part of Microsoft Office. It's generally not a baseline part. You're gonna have to pay an extra 30 or 40 bucks for it, depending upon your situation with your university. But we use Visio now exclusively for our P&IDs. In terms of once you make your list of components, we do that in a spreadsheet. And so you can, we basically have a column for what I just called them valve 1, 2, 3, 4, 5, right? What we have evolved to is a valve numbering scheme, to where if it's a manual valve, the first designator on the valve is MV for manual valve. And then we do a dash, and then what the fluid that goes through the valve. So we have an MV N2, MV FU for fuel, MV H2 if it's hydrogen. There's obviously, we do MV H2O if it's water. And then the next designator is a number. So every component can have a unique identifier. Different places I've worked, I was passionate about exactly what the numbering scheme should be. I may or may not have gotten my way, and after 6 months of using it, it was what I was used to, and that's what it was. When I came to work at Purdue and we had this conversation with students to come up as we formalized things, students argued with me about what the numbering convention should be. I'm pretty certain they were probably arguing for what I had wanted previously, but it was no longer what I was used to. So I decided, okay, it's not a big deal as long as you pick something and have a reason for it and remain consistent. And then, so we have an identifier, we have what the fluid is, what the max pressure of the system is, what the max pressure capability of the component might be, part numbers, vendors, etc. And it's a great idea to be rigorous in documenting that, because you're going to be handing that document off to the next group or sharing it as you evolve.
Is there a price amount
The question is, should you minimize the number of fluid system components in your system, or over-engineer for every possible scenario. In my opinion, simpler is the absolute best way to go. All valves are going to fail. All valves are going to need maintenance. All valves cost money. So if you can come up with a reason to leave valves out of systems, I would absolutely endorse that. What we found with we had a group at Purdue in SEDS that build a rocket and the ground support equipment to compete in the the Friends of Amateur Rocketry Mars launch competition. And so the first cut at the plumbing and instrumentation diagrams had, I think, probably twice as many valves as what we ended up with at the end of all the reviews, okay? And a lot of times valves were added to the system with the rationale being safety, okay? Well, we definitely want the systems to be safe, but as you add components to your PNID, you need to write down why you're adding it, what the scenario is that it's actually going to do to either improve safety, provide function in your system. Safety in and of by itself is not a reason to do anything, right? We want systems to be safe, but to change or add something to say that it's safety isn't a reason. There has to be a reason why it improves safety.
Hey, so quick question. On the PID that we had before, there was a valve upstream of the cavitating Venturi. So would that be completely necessary? I was just asking out of curiosity. What was the purpose of that valve again?
Okay, so the purpose of valve 2 in the system was part of our system requirements was to be able to terminate a test or cease propellant flows in the event that the test article fails, which could damage the run valve. So valve 2 in the system, because we've got a tank that's large enough to flow for a significant period of time, we need a valve at a remote location that lets us terminate the flow if we have a failure at the test article. If your run tank only holds 10 seconds worth of propellant, you might have a reason to decide that it's not necessary to have an isolation valve at your run tank. Okay, yeah, every valve needs to be evaluated for how it is in your system for your scenario. So if your propellant system is relatively small, such that if you have a failure, all your propellant's going to be gone within a second anyway, there's probably not a reason to add the isolation valve. Another question?
Yeah, so if for the drain of the lock system, you can just like let it evaporate on like concrete with a lot of water and stuff. What if you're not feeling prepared? What would you typically suggest for draining of the run tank? Like where to put it?
Okay. So in an emergency, so in terms of the normal. So the question is, I showed we showed the LOX chill dump in the system. So the question is, if it's not a cryogen, if it's a storable propellant, what might you want to do with? So it's going to be very propellant and system specific. Okay. If you're running a test with gaseous hydrogen, which we do here, we have high pressure hydrogen tanks. We elect that if the test article fails, we don't want to vent the hydrogen. We want to keep it in the tank. Okay. So we try to put the tank in a safe location such that could be the case. If we test with hydrogen peroxide, our failure mechanism is to leave the hydrogen peroxide in the tank, but to vent the tank. Now we do have a dump. If we test with hydrogen peroxide, we have a thermocouple in the bottom of the tank. If the hydrogen peroxide, if we see any indication that there's a reaction occurring with the hydrogen peroxide in the tank, which we would see by a change in the temperature of the fluid, then we have a dump valve that we can actuate that dumps the hydrogen peroxide into a large container of water so that we dilute it from 90% to as low a concentration as we reasonably can. But certainly, we're going to shoot for at least 30%, to take it below 30% concentration.
So just really quickly, I know hydrogen peroxide is a hot heat, so the reaction can take a while. Is that the same case with nitrous oxide, or is it pretty much breakdown?
Okay. I don't know anything about nitrous oxide. We have not used it specifically here. We have used nitrous in very small hybrids with, say, quarter-inch tubing, but flowing nitrous at any significant thrust level, I would be going to someone else for expertise to understand how best to work with nitrous. We made contact with some engineers that are currently at a company called Parabolis, who were formerly Space Dev, and so they were involved in the development of the X Prize rocket that Rutan and company flew. And so Frank provided all kinds of links to safety information and compatibility information, those kinds of things. And I guess, Adam, what's the plan to share that information with the teams, et cetera?
I think there was going to be some discussion of that as part of the chemical safety section. I haven't seen those slides, so I don't know how in-depth that's going to go, but I've got all of the more detailed nitrous info. So if anybody is using nitrous and would like that as supplementary information, we will definitely make that available.
So hopefully this illustrates that it's absolutely okay to say, I don't know. There's definitely issues with nitrous based on scale. Okay, what velocities and things that can work in small lines can create tremendous hazards in larger systems. And a lot of that's just because nothing is actually one-dimensional, which is how we all think about flows. And the larger the plumbing gets, the more opportunities there are to have a big distribution or variation in what's actually happening with the propellant.
Yeah, another really interesting factor with nitrous oxide is that it's an amazing solvent for hydrocarbons. In fact, there's been some recent studies that have suggested it's one of the best known solvents for hydrocarbons. So unlike something like liquid oxygen, where if you do have some contamination in it, obviously this is a dangerous situation, but it's at least not going to tend to dissolve in the LOX, whereas with nitrous it can. And so that over time can lead to significant, intimately bound up contamination that could be a massive hazard. So the cleanliness aspect with nitrous oxide is every bit as great as it is with LOX, if not even more.
So I talked about having a formal process to change your system design, to make sure that that you put as much effort into reviewing any changes as you do into the design in the first place. Once you have assembled your system, we have found it to be extremely helpful to have someone that's knowledgeable of fluid systems take your plumbing and instrumentation diagram and audit your system to make certain that what was built is actually what you designed. we've had all kinds of interesting test not so much, we've been fortunate, we haven't had full-blown failures, but we've had unexpected performance of installed systems on some of our test stands. And it turns out it's because, the person that was working on doing all the plumbing and putting the system together had basically read the PNID wrong and internalized it in their brain. And so when they looked at the PNID, they never saw what was different relative to what they interpreted. And a purge line was connected to the wrong place, or a check valve was just simply installed with the, going the wrong direction. Things like that. It's very, very important and critical to identify before you try to operate the system. Generally speaking, we found those during leak checks. It hasn't gotten to the point of when we actually try to attempt flowing propellants, but it's happened. And so having a third party that's not a part of the system in the first place, or not their primary role, do an audit is extremely valuable and helpful. That was the extent of the content that I had prepared for the system safety. Thank you guys very much for your questions during this. I'm not sure where we are schedule-wise. I think I'm quite a bit ahead of what had been allocated.
We are a bit ahead. Adam, do you want to go ahead and start your section?
Sure, I could either start it now, or if I know we had a 15-minute scheduled break, I think. So if people would like, we could do that and then jump into mine.
So we can take the break now, but I have food arriving for us here.
Oh, okay.
Time. So if we could do like the first 15 minutes of yours, I think that would be great, and then take a break.
Yep. Yeah. Absolutely.
Excuse me. There was actually a question I had about leak tests.
We have a question on this side for Scott. Do you want to come up here and ask your question?
Hold on 1 second. He's coming.
Okay.
You mentioned at the end about when you're performing leak tests. How exactly do you perform leak tests on systems like this?
We perform leak tests with an inert gas. The system didn't, I didn't go into a complete PNID for a propulsion system, but generally speaking, for static tests, we're going to have purge circuits. So through a combination of the inert gas that pressurizes the propellant tanks and or the purges, we introduce pressure into the systems in order to perform the leak checks. Our process for leak checking upstream of the run valves would be to use the propellant tank pressurization systems to accommodate that. And so what we'll do is, as remotely as possible, we'll pressurize to 50 psi. Once we let the pressure stabilize at that pressure for a couple of minutes, we will then go and use soap solution or Snoop to look for leaks. Once we've accomplished that, looked for leaks, if we find any leaks, we isolate the pressure supply and vent the pressure, and then manipulate fittings or tubes or whatever's required to fix the leak. Once we've accomplished the thinking we fixed the leaks, we'll vacate the area again, bring the pressure back up to the 50 psi, look for leaks. If we pass at 50 psi, we vacate the area and bring it up to 100 psi, wait for it to stabilize, come back in, and repeat. Generally speaking, we're going to go up to, we'll leak check up to about somewhere between 50 and 75% of the intended max rated operating condition. not the max capabilities, but the actual intended operating condition. When it comes to leak checking test articles, we will generally design a leak check plate that can be installed across the nozzle of the test article. This is something that you're going to have to be very, very careful of relative to liquid propellants. If you're using kerosene, you've got a fluid there that's going to want to contaminate your system in a huge way. So we always leak check by bringing the inert gas in through the oxidizer manifold. We want to make sure that as we're bringing pressure into the combustion chamber, we're not allowing anything from the combustion chamber or the fuel injector manifold to get into the oxidizer side of things. So we're going to want to have purged, and hopefully you're leak checking with perfectly clean hardware before you've ever flown any propellants. But you always want to bring the pressurant for the leak check in through the oxidizer side of the system. The leak check plate that you install in your nozzle needs to have a hole and a valve. Okay, once you pressurize your combustion chamber with your with your oxidizer and fuel injector manifolds all together, you pressurized a volume with the gas that is not suitable to go back into either of your propellant systems. You want to be able to vent that gas out through the nozzle in the same direction that it would go if it were a combustion test. So same drill, close the valve on your leak check plate, on the outlet of your leak check plate, bring it up to the system up to a low pressure remotely, let it stabilize and make sure it holds without any issues before going in and doing the attended leak check. If you find a leak, you don't ever try to fix them under pressure. You clear the area, isolate the source of the pressure, vent the pressure, fix the leak, and recycle. And step up to, you're going to have to have decided ahead of time, based on what you hydroproofed your hardware to, what the safe attended leak check pressure will be. But I would expect it's going to be on the order of less than half of your intended operating chamber pressure. Once you finish your attended leaks, the only leak check you can do above that pressure will be to bring it up to pressure, isolate the supply, and then watch for pressure decays on instrumentation.
What is your say like right? A lot of times it works. What is your process for figuring out what exactly?
It's injecting. It's basically spraying a soap solution on the outside of your plumbing and looking for bubbles. You can buy that solution that's intentionally made for that. It's called Snoop, and it's sold by Swagelok. And they will sell a version of Snoop that is not supposed to create issues in terms of contaminating oxygen systems. Just a second, I got somebody online saying something.
Quick question. For lock-safe cavitating Venturis, is there any particular suppliers that you guys have found have been reliable and not like break your budget?
We purchase all of our Venturis from a company called Flowmax. Flowmax is spelled Flowmaxx. Flowmax is owned by Stuart Cole, and I'm pretty sure that Purdue are his best salesmen. But generally speaking, the Venturis look like I mean, he'll make them in whatever type of in connections you want, but for the most part, we buy them. They look like an AN tube union. They're a little bit long, but they'll have male 37-degree flare ends on them. And just FYI, what we do is we will size the throats of the Venturis. We'll determine what the size of the Venturi should be based upon our intended, what the fluid is, what the pressure and temperature of the fluid will be. And then we'll provide we'll basically tell Stuart, okay, we need a Venturi that will provide this flow rate with this propellant at this pressure and temperature. And we calculated the throat size to be this. And Stuart will independently make the calculation and verify that for you. And if you're like us, he'll always change the size of the throat by at least 1 thou, just to show that we weren't quite on the moon. But basically the throats are only sized to the nearest thousandth of an inch. It's not really practical to size something to a tighter tolerance than a 1,000th of an inch. So the question is, larger tubes are more expensive. Would it be better to accommodate the flow rates with multiple tubes? I don't think you're going to find it to be less expensive to do multiple tubes. Tube fittings are very expensive. And if you're going to have a valve that controls the flow, you're going to have a lot of expense in adapting multiple tubes to a valve compared to just doing one tube. I think that's what's going to trade out that way.
And remember as well that each connection is something that can leak.
Yeah. You're looking to make your life miserable to do more tubes.
My earlier comment about the snoop thing, we literally
Gotcha. Yeah, instead of buying Snoop, if we use soap, we prefer palm olive unscented dish soap. Or the palm olive original, the green. That's also our first go-to soap for cleaning things. I'm sure we're going to get into techniques for cleaning and so forth, but the simpler the better with respect to cleaning. And so the first line to remove machine oils and things can be an effective surfactant, such as dish soap. Another question.
Yeah, what's the best way to model the effect of protective barriers on glass gauges?
Well, you've got the right keyword. If you're looking to design things for explosions, if you look for explosion and detonation and things like that, you will not find things. Blast is the key word. All of that evolves from DoD things, and it's all, you basically relate your worst case release of gas or combustion to an equivalent C of TNT, and that's the way all the tables are set up. If your organization meets the requirements to be able to purchase documents from CPIAC, there's whole manuals on structures to resist the effects of blasts. And you have two things to protect from, right? One is the pressure wave, which is very easily done by distance, and the other is protection from fragments. And for the most part, failures of rockets and things, they're not fragmenting in ways that are going to more than likely travel very far, like a ballistic projectile is designed to do. But you'll find some recommendations and guidelines in those documents.
Hi, I have a quick question.
Yes.
So, in terms of fuel systems, like let's say even alloys or propellant, what kind of fittings do you think that you can suggest? Like there are different kinds of fittings, like AN fittings, UNF fittings, and PT fittings. What kind of fittings do you think would be? Because some fittings have torque values on them, but some fittings do not have torque values, like NPT fittings that I could find. So, what do you suggest in terms of fittings to make sure that the plumbing is safe?
We'll be getting into some of that actually in the next section. So I don't know if we want to go into that now or.
Why don't we go ahead and since you have a whole section on that, Adam, let's hit it then.
All right, sounds good. And incidentally,
I've got one more question here, Adam.
Yep.
I just you guys have used
So the question is relative to the determining the worst case explosive failure in terms of coming up with quantity or distances and shielding. Our calculations, I mean, we're very fortunate here at Purdue in that we have facilities built to resist blast. So we don't typically, we basically limit the thrust class of what we do so that we're well within whatever it is that we're doing. Most of the time, the worst case scenario is going to be a failure of the propellant system that allows the large quantity of propellants to mix. If you have an explosion that damages your thrust chamber, that's largely going to be, that energy is going to be taken up by the failure of your thrust chamber. So that's going to be a fragmentation or type of thing, not so much a pressure thing. Most of the time, certainly for static tests, we're generally going to have something bolted together on our rocket engine. And we are basically going to design the bolts to yield and fail before the chamber fails in hoop. And so we basically will chuck the nozzle intentionally before we have a burst of the test article.